Welcome everyone to a session on automata theory and computability. In this session, let's solve few more problems on PDA for the given context-free language. So we'll take the first one. Here the language L is made up of string W from the alphabet symbols closing bracket and opening bracket, and star represent any occurrences of these two symbols. And the definition of the language says the parentheses are balanced. So what do you mean by that? So this means there should be equal number of opening and closing bracket. Okay, so if I get a string epsilon, okay, so if I don't have any opening and closing brackets, then this is totally fine because we have a zero number of opening followed by zero number of closing brackets. So this is accepted. So what about this one? I have a single opening followed by a single closing bracket, so this is also valid. Okay, so this is a problem where we have to match equal number of opening and closing bracket, provided there should not be any closing bracket appearing before we encounter opening bracket. So if I get something like this, so this is also balanced in some way. Balanced in the sense here the number of opening bracket is equal to number of closing bracket, right? But this is not accepted by the definition of the language because I have encountered closing bracket before I encountered an opening bracket, right? You consider a simple programming language where we require equal number of opening and closing brackets, provided the opening bracket should appear before we encounter a closing bracket, right? Okay, now what approach we can have? Again, we can have a very simple approach. So what we do is, for every occurrence of opening bracket, we push an element onto the stack. Okay, so let me push X onto the stack, or let me make use of the same symbols. Okay, let me push the opening bracket onto the stack. Okay, and so I am performing push operation. Okay. And for every occurrence of closing bracket, I'll perform a pop operation. So what will be the content of the stack? This is popped out, right? When I encounter opening bracket, I pushed it into the stack, and when I encounter closing bracket, I'll perform a pop operation such that the stack will remain empty and I should be in some accepting state, right? So using this approach, let us construct a PDA. While constructing the PDA, first let us consider the simplest string that is accepted, so which is epsilon. This contains zero number of opening and closing bracket, so this will match to the definition of the language, right? Okay, so I'll start the machine in Q0, which happens to be the starting state, and on the right side I'll write the content of the stack, which will remain empty. So when encountered with epsilon, the content of the stack is empty and the machine will remain in Q0 state, which is marked as accepting, right? So this is totally accepted. Now if I consider single opening and closing bracket, which is also valid according to the definition. So as previously seen, what we will do is, for every occurrence of opening bracket in the Q0 state, will perform push operation, right? So opening bracket symbol is pushed onto the stack and will remain in Q0 state. Now when encountered with a closing bracket, will perform pop operation. Popping what? Popping the top of the stack element, which is opening bracket, right? Okay, so this, after popping, this will be the content of the stack. So for the first opening bracket, I have performed push, and for this I have performed pop operation. So equal number of push and pop results in empty stack. So this satisfies the condition for the PDA. It is in an accepting state Q0, and also the content of the stack is empty. Now if I take another example, let us see what will happen. So the first occurrence of this opening bracket, I need to perform push operation being in Q0 state. Okay, so I'll perform push and I'll remain in Q0. For the second symbol, which happens to be a closing bracket, I'll perform pop operation. So second symbol here is again an opening bracket. So again I have to perform a push operation, right? Okay, so one more push. So this will result in pushing opening bracket onto the stack. So this will be the content of the stack after encountering two symbols on my string. And the third symbol, it happens to be a closing bracket. So what we do, we perform a pop operation. So when I perform pop, this is the content of the stack. And finally, for the last symbol, which happens to be a closing bracket, we'll perform a pop operation. So this will result in empty stack, right? So this is also accepted by the PDA. Now let us take an invalid string. So what will happen in this case? So when I encounter a closing bracket before an opening bracket, so we don't have definition, right? So what need to be done? Opening bracket, closing bracket, when the stack is empty, we don't have a definition. So Q0 machine doesn't know what to do. So such kind of string will be totally rejected. So this will result in some dead configuration and the string will be rejected. And if I have mismatched number of opening and closing bracket, this will result in non-empty stack, right? So in this case, I'll be pushing two opening brackets, and for the occurrence of closing bracket, I'll perform a pop operation. This will result in a non-empty stack. So this will also be rejected by the PDA. Now let us see the various tuple values for this particular PDA. Now let us write the tuples value for this PDA. So starting with K, which is nothing but the set of states. So since we have only Q0, the content of K is Q0 itself, followed by the second tuple, which is alphabet symbol sigma. We have opening and closing bracket. Third being the stack content. So here we made use of a stack element as opening bracket to perform push and pop operation. Then comes S, which is nothing but the starting state, happens to be Q0. A, which is a set of accepting states, will be Q0 itself. And finally, for the transition, delta Q0 upon opening bracket, we do not perform any pop operation, and the transition will happen to Q0 state itself by pushing opening bracket, right? So this will be the transition for opening bracket in Q0 state. And one more transition, Q0 when encountered with closing bracket will perform pop operation, will remain in Q0 state by not pushing anything, right? So this will be epsilon. This will be the tuples value for this particular PDA. We will solve few more problems. In this problem, the language L is made up of string W from the alphabet set AB, and the definition of the language says number of A's occurring in W should be equal to the number of B's occurring in W. And so in other words, the number of A's should match with the number of B's irrespective of their order, right? If we get such kind of strings, then it should be accepted by the PDA. So let us consider some examples. Okay, if I consider epsilon, yeah, this will contain equal number of A's and B's. right? So epsilon is the smallest string that should be accepted as per the definition of the language. What if I have AB? So this has one occurrence of A and one occurrence followed by one occurrence of B. So this is also accepted. And what if I have BA? Even this should be accepted. Here I have encountered B first followed by A. So even this is accepted. ABBA. Yes. So here also I have A, one occurrence of A followed by two occurrences of B and ending with another occurrence of A. So totally two occurrences of each character. So even this should be accepted. Okay. So what approach we can have is, for every occurrence of A, I will push an element onto the stack. I'll push A onto the stack, and for every occurrence of B, if the top of the stack happens to be A, then we'll perform the pop operation. And the same is applicable with the other case also. That is, for every occurrence of B, I'll try to push B onto the stack, and for every occurrence of A, if B happens to be on the top of the stack, I'll perform the pop operation. So this kind of solution is highly non-deterministic. So for every occurrence of A, I'll perform push operation and pop operation simultaneously, right? And for every occurrence of B, I'll perform again push and pop operation. So every occurrence of a symbol will give me two multiple paths, right? And while constructing the PDA, we should worry only about the path that will lead me to the accepting state or accepting conditions of the PDA. Okay, so keeping this approach, let us try to solve the problem. First, I'll write the transition diagram. So let me name it as Q0. Okay, and on the right side, let me mention the stack. So this will be the content of the stack initially, okay, which is empty. Let us consider epsilon. So if I consider epsilon, which is valid according to the definition, then Q0 should be marked as accepting, right? So when you encounter no string at all in the starting state, which is accepted, then you should mark starting state as accepted. Okay, so this Q0 itself will be accepting, and the stack will remain empty because no push or pop operation has been performed. So this will satisfy both the conditions of a PDA, ending in an accepting state and stack being empty, right? So epsilon is accepted as per the design of our PDA. So this is fine. Now let us see what I can do with AB. Yeah. So for every occurrence of A, I am considering this example now, the second one, AB. This is the example what we are considering. For the occurrence of A, what we are supposed to do is we need to push A onto the stack. So when I encounter A, I have to perform a push operation. So I'll be pushing A onto the stack. And for every occurrence for the we are done with A. Now we'll encounter B, right? So for every occurrence of B, if A is on top of the stack, then I'll perform pop operation. For B, if A is on the top, then I'll perform pop operation. So what will happen? The content of the stack will be empty, right? So this A is popped out. So will this be accepted? Yes, this will be accepted because we have remained in Q0 state, which is an accepting state, and the stack is empty. So what we have done is, for A, we have pushed A onto the stack, and for occurrence of B, we have popped A from the stack. Right? Okay. Now let us consider the next one. What if I have BA? So in this case, for the occurrence of B, I will perform push operation. For when I encountered B, I'll perform push. So what I'm pushing B onto the stack. So in this particular problem, we require two stack symbols, A and B. So this is because we have to match the number of A's with the number of B's, right? So we make use of two separate symbols. For every occurrence of A, I'll push A, and for every occurrence of B, I'll push B. Okay, so this is what I've done. Now B is done. Now what if I encounter A? When I encounter A, what am I supposed to do? I need to perform the pop operation. So I'll remain in Q0. A, when encountered with A, if the top of the stack happens to be B, then I'll perform pop operation. So what did I end up? I ended up in an empty stack, and I'll remain in Q0 state. So both the conditions for the PDA is satisfied, right? So as previously said, this is non-deterministic. For every occurrence of A, if you observe, here I'm performing push, okay, and the other path will perform pop operation. And same is applicable with B. So for every occurrence of B, I'll perform two operations, and one path of this non-deterministic approach should lead me to an accepting conditions, right? So here I perform push, and this is the one for pop. This is a highly non-deterministic PDA, right? Now let us take the last example, ABBA. Okay. For the first occurrence of A, what I will do, I'll perform a push operation. So A is pushed onto the stack, and I'll remain in Q0. For the next occurrence of B, I'll perform pop operation. This A is popped out. Of course, the machine goes into another path where B is pushed onto the stack, right? But let us consider only the path that will lead me to the accepting condition. Okay, so I have performed one push and pop. Push, and for the B, perform pop. Okay, now when I encounter B, what I will do, or the machine will do, is it will push B onto the stack. And for the last occurrence of A, this is push. For the last occurrence of A, I'll perform pop operation, popping B from the top of the stack. So this will result again in an empty stack, right? So at the end of ABBA, one path will lead me to an accepting state Q0, and the content of the stack is empty. So this example, this is a valid string according to the PDA, right? And according to the definition of the language also, this is valid. So our PDA works pretty fine. Okay, now let us consider some invalid string. So what if I take ABB? So in this case, A is, for the occurrence of A is pushed onto the stack, and for occurrence of B, A is popped from the stack, right? Then when I encounter A, when the third B is encountered, or the third symbol is encountered, which happens to be B, will perform push operation, right? Okay, so this will be the, after encountering the entire string, this will be the content of the stack, which is not empty. Henceforth, the string will be rejected by the PDA. Of course, it will result in Q0, but we have two conditions. The stack also should be empty, right? Which is not in this case. So this will be totally rejected by the PDA. So this is how the PDA works for this language, right? Okay. Now let us write the tuples value for this PDA. The first tuple is K, which is the set of states in the PDA, which happens to be Q0, since I have only one state. Sigma, alphabet symbols that will be appearing in a valid string, which is nothing but A and B, right? Then comes tau, the stack symbol that is used in our PDA. So this is A and B again. Then comes S, which is the starting state, happens to be Q0. A, set of accepting state, since we have only one, which is again Q0. And finally coming to transition, delta. Okay, so we'll write Q0 upon A. So one operation what we do is push operation, right? So Q0 upon A, I'll not pop anything out, I'll remain in Q0 by pushing A. So this is one path, one transition for Q0 upon A. Another one is Q0 upon A, I'll pop B, Okay, remain in Q0 and don't push anything. Q0 upon B, don't pop anything, remain in Q0, push B. And finally, the last transition, Q0 upon B, I'll pop A out and I'll remain in Q0 by not pushing anything. So these are the tuples value for this PDA. We'll solve few more problems in the next one. I'll see you in the next one.